Okay, so I'm going to do this integral today, 1 over x times square root of x to the fourth plus 1. And I'm going to start by just doing it in a way that you would learn in your average first year calculus class. It can be done. It's a relatively simple integral. But then I'm going to show how to use essentially the Riesz algorithm. I'm not going to use the full Riesz algorithm, but I'm just going to illustrate the basics. It's a more general technique that can handle these kinds of integrals. And well, you'll see how it goes. So let's start by just taking a look at this integral, put it right here. And how might we do this, just like I said, if you were just using kind of like first year calculus. Probably a good guess would be to just do a variable substitution with u squared equals x to the fourth plus 1, and then figure this is going to be the square root of u squared. It's going to be u. And let's just give this a shot, and we'll differentiate both sides, derivate, I should say, both sides. And we'll get this dividing through by 4x cubed, we'll get 1/2 u over x cubed du, right? That looks, yeah, that's right. So now we can take this value for dx and this value for u squared and u and substitute in here. And what we're going to get here is 1 over x u times dx, which is 1/2 u over x cubed du. And as we can see here, the u's cancel, and we can pull out the 1/2, and the x's multiplied together. We get 1 over x to the fourth du. Well, right here we can just rearrange this and see that x to the fourth equals u squared minus 1. So this is 1/2 times a fraction, 1 over u squared minus 1 du. Now we can just do this using a partial fractions expansion. Actually, I already pulled the 1/2 out right here. We can do this using a partial fractions expansion, and it's going to be something over u minus 1 and something over, I'll put the plus here, u plus 1, u minus 1 du. And what's it going to be? Well, we need a u minus 1 here. And actually, I guess for the signs to work out, I guess I'm going to need this here. This would be u plus 1 minus, I'm just looking at the numerators here. What I got to multiply by to get u squared minus 1? This one I need to multiply by u plus 1 over u plus 1. So I'm going to get u plus 1. And I want to subtract u minus 1, and that'll give me negative, be 1/2. 1/2, 1/2. I think, yeah, that's, I'm convinced that's fine. 1/4 integral of 1 over u minus 1 minus 1 over u plus 1 du. And we can do that as a pair of logarithms. I'm just going to do logarithm of u minus 1. I guess we could make that a square bracket just for nesting purposes. I'm not going to use the absolute values here. Of course, we have a plus c. And difference of logarithms, you have just general properties of logarithms. Logarithm of, let's say, uv is the sum of the logs, and the logarithm of u over v is the difference of the logs. So we can see the difference of logs, so we can combine this together, and we're going to get logarithm of u minus 1 over u plus 1. And u squared is x to the fourth plus 1, so just substituting that back in, we will get, this is x to the fourth plus 1 minus 1 over x to the fourth plus 1 plus 1, of course, plus c, and that is what the is one pot. I mean, there's other, we can write this in other forms, but that is what one possible simplification of this integral is in terms of natural logs and the roots. So what I want to do next is take a look at this and see how can we do this integral. Let me put this on a clean board here. What I want to do, let's just take this whole thing, copy it, and paste it. And what I want to do now is I want to show how to do this using using the reach techniques, because yeah, I mean, it's, you look at a square root, it's an obvious guess. You can throw this u squared equals whatever the polynomial is under the root, but that doesn't always work. We have a more general solution strategy that does always work, and that is, first of all, let us I guess we can use u again. We make the kind of the same substitution. U squared equals x to the fourth plus 1, and now this integral becomes 1 over, we're not going to try and play any games with the dx, or we just 1 over xu dx. And we're now going to treat this as a rational function on an algebraic curve. An algebraic curve meaning a curve defined by a polynomial, which is what this is, and a rational function being a ratio of polynomials, which is what this is, the polynomial in 2 variables instead of a polynomial in 1 variable. And first thing we want to do is we want to work on projective complex space. And the primary advantage of projective complex space is that an algebraic function is completely characterized, almost completely characterized, by its poles on a complex. You can actually see it a little bit. You can see this on complex projective space, completely characterized by its poles on complex projective space. Just to complete my sentence, you see something like a polynomial, a rational function. I mean, if you do it expanded out as a partial fractions expansion, you might get something like, I don't know, something like this. And the thing is, you could look at this way. You could say this is 1 over x squared. This is 1 over x. This is 1. You could look at it like this and see and treat these polynomial components, these polynomial terms, as they are poles at infinity. When x goes to infinity, these terms go to infinity. So if you include a point at infinity, rational functions, at least on just 1 variable, are completely determined up to an additive constant, up to this constant 1. The locations, strengths, and coefficients of their poles completely determine them. If you include infinity, that's the projective space component of the thing. And of course, if you have to completely factor the thing, if you want to completely factor these denominators, then you need complex projective space. And there's also an additional requirement, and these algebraic curves can have singularities, so you need a normalized form of the curve in projective complex space. But once you do that, once you work in a normalized curve in complex projective space, the rational functions are completely determined by the locations, strengths, and coefficients of their poles up to a constant. Well, the constant is typically going to disappear as a plus c anyway, so that actually is a pretty general strategy to attack this kind of integral. So let's go ahead and see how. I'm not going to try and do the calculations by hand, but I will use Sage 9 here. Okay, let's put this guy right here, and come down here, and let's fire up Sage. These features are relatively new in Sage. You do want to use Sage 9 to get these features, but let's give it a minute or two to. Actually, probably going to take about 10 seconds to start up, so I don't think I've started it yet on this this time I booted the computer. It takes a few seconds to start. There it is. Okay, so what can we do here? We're going to do this setup. We're going to have this. We're going to do, what are we going to do here? We're going to do, I'm going to start with a function field over QQ bar. QQ bar is the algebraic field and includes all roots of, square root of 2, square root of 3, everything defined by a root of with rational or integer coefficients. So it's algebraically closed. It's not the full complex field, but the full complex field is hard to work with because it's hard to represent its elements. They're too big. You need like an infinite expansion of a complex number to really represent it. So we use QQ bar, which is the algebraic field, and now X is like you can do. I mean, it's just a function field. It's rational functions of X, and now we want to extend it to get U. I will start with a capital U. Is just now. This is just. I'm going to put U squared minus X to the 4th plus 1 because this is now just a polynomial ring in X and capital U, and the reason I use capital U is so what I want to do next, I want to say f of lowercase u is R extension. Basically this is modding out by this this polynomial. So now if I were to use lowercase u, I just get 0. It's f is lowercase u now is f. F is the field. R is also a field, actually. Where is it? No, it's a ring. R is still a ring. But even though it says function field, I think R is a ring. F is a field, and lowercase u is the field modded out by this polynomial here. Capital U is just the bivariate ring. So anyway, we have this, and we can now do 1 over x times u, and it normalizes it by moving the u to the denominator. This calculation is just, what do we got here? This is just 1 over xu times u over u. We get u over xu squared, and we know that this is x to the 4th plus 1. So that's why this becomes u over x to the 5th plus x. That's just a normalization here. All right, but we want to introduce the differential, and the differential is important. One of the nice things I said talking about the poles on a normalized complex projective space, normalized curve on complex projective space, is that the poles are well defined. Why? Because you can do series expansions. But you do have to take the differential into account for the simple reason that you can't always do the series expansion in terms of any one particular variable, in this case x. Like you couldn't do the series expansion here in terms of x when x was infinite, for example. You'd have to use 1 over x, perhaps. So we do want to bring the differential into the mix. It's that's fine. We can do this. We can just take x differential. And now we want to know where its poles are. So we're going to ask the computer to calculate its divisor, which is actually going to give us both zeros and its poles. But here we go. And the pluses, the positive places are the zeros, and the negative ones are the poles. So what this is saying is that we have zeros at infinity when x and also u become infinite. This actually becomes 0 as x goes to infinity. This will be 0. And then we have poles when x is 0 and u is 1, or x is 0 and u is negative 1. That's a little more obvious, I think. Clearly, when x is 0, this can be the square root of 1, which can be 1 or negative 1. And when this is 1 over 0 times 1 or 0 times negative 1, this expression is going to become infinite. So yeah, we have poles there. And we want to now do a series expansion of this expression at those poles. The first thing I'll do, I'm just going to pull out the poles of the divisors. I'm going to say PL and do a, let's say PL for, let's go with, place. Let's say pole places. Pole places is PL for PL and M in divisor converted to a dictionary. And we'll take the items out of the dictionary, which are pairs. Well, let's just, first of all, let's just tell you what this is. This, did I do something wrong here? Extra parenthesis. Oh, drop my 1 over x times u. This. You see the dictionary. Let's just look at the dictionary itself. We have a dictionary that has the locations, the places, and the strengths. 0, 1 for the zeros, -1 for the poles. So I'm going to pull out items. I'm going to say for place and multiplicity in here. I only want the multiplicities that are negative. And I'm going to call this again what I call it. Pole places. I want PL for the places in the divisor where the multiplicity is negative. And though something didn't go wrong. Oh, less than 0, not less than -1. Less than 0. Okay, so there we go. So now we have 2 places, and we want to do series expansions at those places. So let's just see how we would do that. Let's look at the first one. We can ask for the completion, and I thought L was the name, but what I call the function field, F. F is the name of the function field that I defined up at this step here. F completion at the post, we have a completion map, and apply the completion map to 1 over x times u, and it will give me a series expansion. Maybe its default precision is 20. That's probably not such a good idea. Let me stop that. How about less maybe precision 10? That run a little quicker? There we go. Okay. So we see we have a pole. S is a local uniformizing variable. I could figure out what it is, but it really doesn't matter what the exact choice of S is. It is a local. It is a suitable variable for doing a series expansion at this particular place. And we see that it is in fact a pole. There is an S to the -1 here. And then if we were to, well, ideally I'd like to do this, right? But it doesn't work. It complains. Maybe in a later version of Sage, we might get it to be able to take series expansions of differentials. Right now, though, we'll just, we will do this. We will, first of all, I can take the, do the series expansion of x. It looks like S is x at this point. I wouldn't be surprised. And I can differential, is it right? Is it different? I mean, it's not right. I mean, it's derivative. I mean, it's derivative. There we go. Okay, so I can take its derivative. So there's the series expansion. Of course, I take its derivative, and I get 1. And you can just kind of look at this and see that I don't really even, it looks like S is x, and ds is going to be 1 dx. So I don't really have to even worry too much about this, it seems. So, but ideal. Okay, if in general, what I'd want to do here is multiply this by F completion, pole places 0, precision 10 of x, and then take its derivative. That would give me the series expansion of the differential, and not just the integrand here. But like I say, it looks like in this case it doesn't even matter, because I think the x at this place is a local uniformizing variable, and also with the other one too. So what we got here? We have F completion at pole place 1, and let's look at its completion at pole place. I'm sorry, at pole place 0. Now let's look at it at pole place 1. So at the first pole place, our series expansion is with s equals s to the negative 1, and the other one it's at s to the 1. So we have like at what is it? Place. What are the pole places again? The first one is going to be 0, 1, and the second one is 0, negative 1. These are just the values of x and u that make these polynomials equal to 0. So at this place, this is the first one, the series expansion of our differential, our integrand, is 1 over s plus, it doesn't really matter what its higher order terms are. And this one, it's going to be negative 1 over s plus something, something, something. Now, what do we want to do here? What happens when we take the derivative of a logarithm? Let's say log x. The dx of log x is 1 over x, and that's what we want here. We want the derivative of some. What we're looking for is the derivative of some function, and what's it going to be? It's going to be f over df dx, and whatever f is. Let's just say we have f. Let's just say we have a series expansion here. Let's say it's going to be, let's just say C1. I'll make it C2. C2 s to the negative 2 plus C1 s to the negative 1 plus stuff. And then its derivative, I probably should have done that with respect to x, but let's do it with s here. This is going to be negative 2 c2 s to the negative 1 minus c1 s to the negative 2. I'm sorry, this is negative 3, right? And so on. And then when we divide f by its derivative, all I really care about is the leading, the most polar parts, the lowest power in a Lorentz series expansion. This is going to be c2 s to the negative 2 over negative 2 c2 s to the negative 3 plus stuff. And what's that going to be? The c's are going to cancel. I'm going to get, no, I did this. This is the other way. So yeah, I did see, you see the mistake. This is not this. This is df dx over f. These two are backwards. I can just redo this one. This is also written backwards. This is not the derivative of a logarithm. This is the derivative of a logarithm. What do we got here? Negative 2 c2 s to the negative 3 plus higher terms c2 s to the negative 2 plus higher terms. What happens when we cancel everything out? We get negative 2, the c's cancel, and we get s to the negative 1. So actually the actual value of these coefficients doesn't seem to matter, and in fact they don't, because as we'll see, we can just scale this thing. When you're in a logarithm, scaling a logarithm, just see what we did before. Logarithm CF is log C plus log F. So when this is in the integral, log C just disappears into our constant of integration. So when we have a logarithmic result in our integral, we can always just multiply inside the logarithm by a constant, and it just produces a constant that vanishes into our constant of integration. So actually, no, it really doesn't matter what this coefficient exactly is. What matters is, you see, the pole the power of the strength of the pole, that's what becomes the coefficient. You always get an s to the minus 1 term, and then this is if this was an s to the plus, if this was actually, let me just do what can we do here? Copy, and if I were to take all this, copy it, move it down a bit. I don't know what just happened there. Paste it. Yeah, that's what happened there. Here's my C2. C2. Oops. I got here. Tool, pen. All right, so let's, the illustration I'm making here is, let's say instead of a -2, let's just say we had a -1 here. If this was a first order pole in our function f, what would happen here when we divide this? Well, we get df is -c1 s to the -2 over c1 s to the negative. Again, the constants cancel. We get negative s to the -1. So again, we got s to the -1 here. We get s to the -1 here. The strengths of the pole doesn't change. What changes is the coefficient. You see here, the coefficient here actually comes from the power of the function. I'm going to do one more example to illustrate how this goes together. Let's say f is just c1 x plus c. Let's say it wasn't a pole. What if there was a 0 here? What happened here? We got 2c2s, and now again df dx over f. What happens here? Well, we get df dx c1 plus stuff over c1s plus stuff. Again, the constants cancel, and we get 1 over s to the -1. So again, even if there is a 0 in the function, we get a pole in the logarithm, or the derivative of the logarithm. And in this case, notice there is a plus sign here, whereas up here there was a minus sign that goes directly related to this as a pole. This is a -1 in its power, so we have a -1 in the coefficient here. We have a -2 in the power here. We have a -2 in the coefficient there. We have a +1 in the power here, so we have a +1 in the coefficient there. So coming back now to our places here, we see that we have a 0 here, or we have a +1 here and a -1 here. So what we want is we want a function f that has a 0 where we want the positive coefficient, and a pole where we want the negative coefficient. So now what we want to do is we want to construct a divisor. Let me just do this. Yeah, so this, it looks the same, and I'm actually converting it now to a divisor, which is a description of all the poles and zeros for a particular function. So I'm going to take pole places 0 divisor. I'm going to subtract pole places 1 divisor. And now I've got a divisor where I have a 0 positive coefficient at the first place and a negative at the second place. And I think, is that what I want, or do I want them I kind of thought I want them the other way around. The derivative of the logarithm, maybe this is right. I kind of think I want the poles and zeros reversed. That there's like a minus sign that's going to show up here. I think I'm dropping a minus sign here, but let's go ahead and see what happens. We'll call this D. This is our divisor, and now I can really just can we find a function that has a 0 where we want it and a pole where we want it? And that's not a trivial calculation, but we have a built-in function in Sage on our function field code called basis function space. So it looks like we're out of luck. We do not have any rational function on this curve that has a 0 here and a pole here. However, that is not the end of the story. And the end of the story, and the reason not the end of the story, is because let's say I did a logarithm of f squared. Well, that is same as 2 of the logarithm of f. So in fact, if I couldn't find a set of poles and zeros that matched f, I might be able to find a set of poles and zeros that matched essentially a square of f. This f might not exist on the curve, whereas its square, if you will, does exist. And how would I determine, where its square would be? I would just double the strength of the poles and the zeros here. So I can take twice this divisor. I get, second order pole, second order zero. Question: does this divisor have a function on the curve? And in fact it does. And basically this is the answer to the integral. We're trying to integrate I'll write the whole thing out here. Well, actually I'll write it out in xu dx. And what this is saying is that the solution is a logarithm. That's because we're looking at these first order poles and zeros. And what is it going to be? It looks like it's going to be u plus 1 over x squared. Oh, I'm sorry. And I left something out here. Let me just do this. Move this a little to the right, back to the pen. That was the 1/2. Because I doubled the poles, I doubled the strength of the poles and the zeros, this 2 comes over here and becomes a 1/2. So this is 1/2 of the logarithm of u plus 1 over x squared plus c. Now that was not, let's see, what do we have here in terms of our, that was the previous page, that's right. What did we have on the last page? Previous page. What did we come up with here? Combine these two together and I got a 1/2 u minus 1 over u plus 1. Now is this in the same form as this? Let me just take a quick copy of this. All right. So where is our answer? Right here. Here is our answer that we just came up with. This part here, this part here, this being the answer from the computer algebra system, and the question is this the same as this? Well, let's see. U minus 1 over u plus 1, which is this form here, and it looks like the obvious thing to do would be to multiply through by u minus 1 over u minus 1. U minus 1 squared over u squared minus 1, and then or these two should be the same, but I'm not seeing right now why. These I'm thinking these are got to be like equivalent forms here, but what would be the u? We know u squared is x to the 4th plus 1. Let's just go ahead and this is going to be x to the 4th plus 1 minus 1, and this is going to be u squared minus 2 uv. what we got here? Is this what I want? Well, actually, let's not do that. Let's just do this. Get rid of all this. U squared minus 1 is x to the 4th plus 1 minus 1. So this is x to the 4th u minus 1 squared. It looks like we got a square. Basically, this is like a square root. It looks like we're off by a sign and a square. And what is the? Let's go back to the previous page. Was this all done correctly? Oh no! This is a 1/4 here. I pulled a 1/2 out here and became a 1/4 that I proceeded to drop. This is 1/4. This is 1/4. This is 1/4. Where are we here? This is 1/4. So yeah, this is we could do the same thing again. We could if 1/2 logarithm of u plus 1 over x squared is going to be equal to 1/4 the square of the thing in here, and that puts it in pretty much the same form as we got with the other in the more basic calculation. And I do think I'm off by a sign here, and that's why there's a plus sign and a minus sign here. So I might have to come back and look at that and see what I did wrong. But that's the basic outline of how you do a Riesz calculation with Sage. You look at the poles and the zeros, series expansions, find their divisors, find functions that match the poles and the zeros, and that's how you can solve integrals involving Abelian integrals.